Shall we start?
Yeah.
Okay. So, welcome everyone. This is a joint workshop on artificial intelligence in health. My name is Christian Goodman. This is Andrew Costa. We are two of the many organizers of this workshop now. And we will be here. Beatrice is coming. She's another organizer, is that right?
Yeah. Claire is coming, Claire Martin.
Claire Martin is coming, and I think
Isabel is coming in the afternoon.
Okay, fantastic. So, very welcome. I guess we should discuss that. You notice now there is a big queue. There are some issues with the train station. So what is probably going to happen is people are dropping in and they haven't heard this introduction. So we will go through the agenda and so on, but please help out the folks that might be coming later, right? Point them to us if there's any questions when it comes to speakers. Point them to us. Then I would suggest we have also a live broadcast. You're happy to share that. We have that. I mean, at the moment, I only shared it on my Twitter account at the moment, but we can broadcast it and share that one, I would say. Then I think we should go through the agenda a little bit, right?
Yeah. So first, the proceedings will be online during the next week. If you need them beforehand, give me a USB and I'll give the proceedings without the volume number yet, because CEUR has not yet given us the volume number, but they will be online next week.
Yeah, exactly. And so actually we could point out that this workshop now is a joint workshop. So it pulls together the workshop on collaborative agents and research and development. That's something we have been working on for years. It started 10 years ago. Then also the workshop on AI for healthcare, which has also been going on for 10, almost 12 years, I believe,
yeah,
right?
The one I think was new this year.
Yeah.
Because it joins 4 other workshops, which
Yeah.
Which is, what is it,
Agents applied in healthcare, workshop on CBR, so case-based reasoning in health sciences, artificial intelligence in diabetes, and knowledge discovery in healthcare data. And then the third big one is the workshop on knowledge representation for healthcare too. So it combines all those, and part of the reason is that this is, as you probably also know, there is the IJCAI conference, the International Joint Conference on AI, the International Joint Conference on Machine Learning, the European Conference on AI, the Autonomous Agent and Multi-Agent System Conference, and two others. So there's a whole many that have come together, and therefore there were many workshops, and this is one reason why this workshop comes together. And maybe it's also worth noting that it's AI for health. So I'm assuming most of you now in the audience are very interested in this topic. It is something that has really already shown quite a difference. Most of you are aware of the image analysis, when it comes to deep learning and using it for recognition and patterns in images and so on. But it is a major topic. So a number of institutes and countries and companies are investing very heavily into this domain. And when it comes to research, more and more universities are actually making this a specific topic, a specific focus area for them. So I think it's just natural that we picked up the trend 10, 15 years ago, but now it becomes more and more of a reality. And we're expecting about 100 people have registered for this workshop. Again, it's probably delays with transport and the registration. But I think we are at least super excited to have you here. We hope that you enjoy the program. It should be it should still be a workshop style too, so feel encouraged to talk with each other, reflect on the talks that we have. We have many presentations also from students, and that means it's an opportunity for all of us to learn from each other and give feedback primarily, to really push this research forward, I think. Do you have any more reflections?
No, so tomorrow there will be a panel on ethics, ethical issues for AI in health. We encourage you all to come. We will have 3 panelists. He'll be one of them. And we hope to have a lively discussion on that topic as well. And then most of the program today is the paper presentations. And in the middle, so at midday, just after lunch, we have decided to take a break because there will be 2 keynote speeches organized jointly by IJCAI, ICML, and AMAS. And to give you all the opportunity to go see these great speakers, we're taking a break in the afternoon.
Yes.
Yes, there's some papers tomorrow as well. So there's papers today, there's papers tomorrow, and today there's the keynotes, and tomorrow there's the panel. In the middle. The schedule is online. So on our website there's a section which is schedule.
Give me 1 second. Oh, this one. Sorry. It's just I need to go. I didn't know this. Yeah, we have.
Yeah. So this is our morning session right now, which is slightly delayed. If any of the speakers that I don't know about yet have arrived, please let us know. Then there will be a coffee break, and then we will have a second session of talks. One of these is a video presentation. Yeah. So, and then in the afternoon there's the plenary invited talks, and then we have another session of papers, including a demo, which we hope will be interesting.
And just to highlight exactly the plenary talks, I mean, I guess it's obvious, but they're obviously not here. They are in the main hall. And the main hall, actually, is it in B or
A?
Hall A?
Hall
Yeah.
A is big.
So Hall A, and we decided to do so because there's probably a big interest in having those, going to those sessions. Yeah, and then we have the last one, which is about agents in healthcare. And that's like the program today. It's reasonably packed, as you see. We have like 6 to 8 sessions in each of these sessions. And then we welcome you back for the session tomorrow morning. Which starts also at 8:30. It's agents in healthcare. And then we have it from 8:30, first 4 sessions. And then it actually goes all the way to the end, 12:30, and then we close. We probably have some reflections at the end. That's, I think, the main program.
Yeah.
Are there any obvious questions also at this point from you guys? Anything that you wish to ask?
Okay.
No?
Great. Then I guess we invite our first speaker forward to come and present ConvNet. No, ConvNet-based QRS multi-lead delineator in electrocardiogram signals. Good luck.
Thank you. My name is Julian. I don't have much time, so I'll start straight away. A brief recap. Electrocardiogram is a test performed in the clinics to diagnose cardiac diseases. It's performed by placing electrodes at different positions of the body and gives different perspectives of the electrical activity of the heart. Here you can see how a beat looks in an electrocardiogram signal. It's mainly composed by 3 waveforms, the P wave, the QRS complex, and the T wave. In this work, we will focus in the QRS complex, which explains how the electricity is propagated on the activation of the ventricles, and therefore can be used to analyze cases of fibrosis or to detect scars on the heart by analyzing this section of the beat. Okay, so in this work we are targeting delineation, although previous research mostly has started detection. So let me start from that. So detection of the QRS mainly focuses on the R peak, on the features around the R peak, and the target is let's locate the QRS on the signal overall. But in this work, what we are trying to do is to position specifically the QRS onset and offset, so it will enable us to calculate metrics such as the QRS width, for example. And previous works that target this are mainly rule-based systems, so they have to account for every different case. As you can see here, there's lots of variability in QRS in ECG recordings, not only intra-patient but also inter-lead variability and inter-bleed variability, and therefore methods which were designed for specific databases are difficult to adapt to new cases that were not considered in the design. So on this project, what we want is to design a morphology and database independent QRS delineator. And this would serve to to build on top of it diagnosis systems, which are more interpretable by experts. And our hypothesis is that deep learning would be able to extract features which are generic across different databases when trained with appropriate data. So as this is the first step towards this goal, is this ongoing project, we decided to use the Qt database from PhysiNet, which is an open database that has been broadly used for this purpose of delineation in electrocardiogram signals. It comes very handy because this database is composed by recordings from 7 different databases, and therefore we were able to perform Live1 database out cross-validation to assess more or less how it works in different databases, on training on different databases and testing. Sorry. So in this database, we have 3,600 delineated QRS complexes, which come from 105 2-lead ECG recordings at 250 Hz, manually annotated and corrected by 2 experts. Okay, this is here you can see our method. It's mainly composed by 2 parts, the segmentation part and the delineation part. In each of them, we have 2 machine learning models, a convolution neural net and a neural net, which are very similar from one part to the other. Okay, so I don't have time to explain the training, but when this method is already trained, what we do is we take the entire recording, we feed it to the segmentation, and the segmentation part, what has to do is to locate and kind of segment. So it does like the detection task. So it positions where the QRS is on the signal and takes a subsample that you can see here on the right-hand side. No, you're right. That you can see here, it's subsampled from the original signal, but just accounts for the QRS complexes. So we don't have in the second part of the algorithm, we don't have to locate the QRS because it has been already located, and we only are focusing on the QRS onset and offset, which brings a boost in performance, doing it in 2 steps instead of targeting the whole step at once. And this is performed using one hotel encoding. So it works similar as segmentation for deep learning. Okay, so to assess our method, we calculate the same metrics as the state of the, as the related work does, which is the mean of the error and the standard deviation of the error. We calculate this by using Live1 database out cross-validation. And it's worth noting before analyzing the results that our method, so the database has 2 leads on it and has just one delineation mark for both. And we don't know to which lead corresponds because there's no information on that. So the previous work, Martinez, the work from Martinez et al., they had a wavelet-based QRS delineation, ECG delineation, and El Bote was divided in different stages, so they performed different analysis. But they both were single lead, so they both produced 1 mark per each lead. So they have 2 predictions for the same QRS complex. For the onset, 2 predictions for the onset and 2 predictions for the offset. And then they keep the one that gives them higher accuracy when they have to report results. And as we only have one mark, we believe that this may affect our performance when compared to them. And it does somehow. So here, just as a reminder, we have the onset and the offset of the QRS complex. And this is the results for the mean of the error on the onset, the mean of the error on the offset, the standard deviation of the error on the onset, and the standard deviation of the error of the offset, which you already can see that here we have slightly worse, considerably worse light performance. But taking into account the differences in how the metrics were calculated, we believe that this is comparable. So as a summary, we will then train a QRS delineator based on deep learning system techniques. We validate our models on data from 7 different databases. We think that our results make suggest that our model is comparable to the state of the art, and this is an ongoing project. So now we are collecting new databases, perform a deeper validation of our model. And that's it. Thank you very much.
Yeah, thank you. Do we have time for some questions? Or we have time for some questions. So if there are any, yes?
I didn't see if you mentioned that Angela and his students at Stanford's work on arrhythmia detection. Did you mention? I didn't see that. Is it something similar? Can you do the
for arrhythmia detection?
Can you use the same network for QRS detection too?
So arrhythmia detection would be like a further step. So we are like this would be considered like pre-processing in arrhythmia detection. Arrhythmia detection would be like a more abstract, or like a more final procedure you would do. This would allow you to do arrhythmia detection based on biomarkers, which are, so this would give you the onset and the offset of the waves, and then you can calculate biomarkers, and then you can perform arrhythmia detection based on these new biomarkers.
Are you aware of this paper you published a year ago?
Of arrhythmia detection from Stanford.
Yeah, yes.
I have seen many of them. Like, yes. Okay. I don't know. You can send me later the paper, and I will take a look at it. Sure.
Sounds like a natural connection point here. So we should have a discussion. Any other question? Yes.
Have you tried your network on ECG signal acquired in an MRI scanner?
It is the signal acquired in an MRI scanner.
Because inside the magnetic field of an MRI, you have huge distortions of the ECG, and it's quite difficult to detect the QRS complex. So maybe it would be interesting to see how it works with your method.
This sounds really interesting. No, we haven't tried it, but I will keep it in mind and tell it to my team. Sure. Thank you.
Fantastic. Good. Yeah. I think thanks again. The next speaker, please. And you have your laptop. Fantastic. Okay, so the next speaker is Jeremy Weiss. Is that correct? Yes. And you will be speaking about bi-cluster phenotyping of healthcare providers.
Great.
Fantastic.
Thank you very much. So I'm Jeremy Weiss. I'm an assistant professor at Carnegie Mellon University. This is joint work with Nate Fillmore at the Boston VA and the Dana-Farber Cancer Institute, and Ansh Mehta at University of South Alabama. If you want to take anything away from my talk, it's that we are producing a clustering method based on an autoencoder with a clustering module for sparse count data. And what we're using this for is organizing physician practices with health utilization data. Okay, so health providers have distinct practice patterns. And what do I mean by practice patterns? I mean the actions that they take, the prescriptions that they give, the procedures that they do, things, but it goes beyond that. It goes into how much time they take with the patient, who they refer their patients to. And there are definitely things that are associated with that. For example, where did they train? What residency did they train at? What institution are they at? Does that institution have particular policies about the prescriptions and procedures that they can perform? And then does that institution have access to particular resources, for example, urgent and emergent care? And so the goal of this talk and this work is to categorize providers in terms of this care that they provide. And the care that they provide for this talk is going to be the proxy of the prescriptions that they provide and the procedures that they perform as defined by what's available in Medicare claims data in the United States. And so typically, in the United States, we have the National Provider Identifier, the NPI, and that's one per provider, like a physician or a nurse practitioner, for example. And the best indicator, probably single indicator for what they do is where did they do their residency? So you know that the type of care that an anesthesiologist provides is likely to be very different from the care that like a urologist provides. Okay, so what we're going to do is take the phenotype as defined by the prescriptions and procedures they do to try to cluster these groups into better groupings, essentially. Because, for example, internal medicine is very broad. It's not, if you get that as the residency that they did, you don't really know what kind of care that they actually provide. Okay, so the data that we look at is from the Center for Medicaid and Medicare Services. It's the Part D prescriptions, the medications they provide, and then the procedures that they perform. This is, again, sparse count data. Just to give you a sense of this data, it's publicly available. It's got 1 million providers, 6,000 procedures, and 2,000 prescriptions. Okay, so we're going to develop a neural network that does clustering. And the idea here is that we want to take into account the fact that we've got sparse count data. So classic clustering methods oftentimes will not work well because it's sparse count data and Euclidean distances are not going to work well. Also, clustering methods that use medoids are often not going to work well because averaging over members within that cluster isn't necessarily representative of the other individuals. So here's our neural network. We've got an autoencoder, which is the mapping from I to H to O. So the input is going to be a sparse count vector. It's going to be represented by a latent H. And then it's going, the goal for the autoencoder is to reconstruct the input so that we're trying to reconstruct this sparse count vector as well. And so how do we get clusters out of this autoencoder? Well, we introduce a clustering module. That's the connection between H and C. And we need to use some geometric constraints so that we can actually get meaningful cluster probabilities in our cluster vector C out of our latent representation H. And so our particular instantiation for the architecture is in the table on the right. And all you really need to look at is at the very bottom, where you've got this soft max output, which means that C is going to be a probability vector that sums to 1. And so the reason that we can actually get meaningful probabilities in a cluster vector is because the square root of a probability vector is going to have unit norm. And what we're going to do is constrain our hidden representation to be on the surface of a unit norm ball. And so that's going to allow us to connect a probability vector with a latent representation that just happens to be on the surface of a hypersphere. And so all we need to do then is to introduce a loss function that says H needs to be on the surface of a hypersphere, and C needs to, and we also need to minimize the angle, essentially, the cosine similarity between C and H. Okay. So that tells us what losses we should introduce. So we need a reconstruction loss for the autoencoder. We need H to be on the surface of a hypersphere, and we need to match the cosine similarity between the square root of C and H. Okay. There are a couple of other loss functions that we introduce. We think that these help with optimization, and we can show in experiments that these additional loss terms also help us. They involve relationships between H and O. We want cluster entropy, we want the probability of membership to any one of the clusters to be probabilistic, and we want hidden representation to be spread out on the hypersphere. Okay, so briefly in simulations, we generate data. We generate centroids on a unit norm hypersphere, and then we sample data points from with multivariate Gaussian noise around those centroids. And then what we do is multiply by a scalar vector to explode these points away from the origin so that we're really getting the angle of the important part of our clustering method. And then we perturb the particular values that are all bolded into different simulations, and we compare our method versus k-means, and then hidden k-means, which is basically k-means on the hidden representation. And there have been 2 papers in ICML in the previous 2 years that have basically taken this approach. Take an autoencoder, produce a k-means clustering module that's right in the middle. But this is a way to do that without having to do these centroids and updating the model and then updating the cluster centroids. Okay, so our method works better on a number of different metrics, and there's just a bunch of numbers here. Can you guys see that? Yeah, so this is a picture of the bi-clustering we get on the real data. So on the x-axis, we've got the providers, and on the y-axis, we've got the prescriptions. And what you would hope to see in this bi-cluster plot is that we get little boxes that don't really overlap either in the x or the y coordinates. And you can see in the top left that in fact we are getting some of those little boxes that are that show that we've got relatively good clustering both over physicians and over prescriptions. And then we can take a look into histograms of particular clusters that we identify. So we can do several different things with these histograms. So first of all, we want to do a sanity check. We want to verify that we're identifying something meaningful. So here we've got pulmonary disease. So pulmonologists are going to be the primary member in this group, but there are also other related specialties that are also populating in this group. So for example, allergy and immunology, critical care medicine, these are the physicians and providers that would take care of things like asthma and COPD, classic lung diseases. Okay, you also can take a look and see what do providers do if they're not, if their specialty is not really very informative. So if you take a look at this histogram, you're probably saying, oh, this is definitely an emergency medicine cluster. But then you see that we have NPs and PAs who are also here in this cluster. And these are the NPs and the PAs who are probably staffing the emergency department. So we don't actually know that a priori, but we can look at the procedures and the prescriptions that they provide to tell that, oh, these are the NPs and PAs that are providing that type of care. That's as compared to the orthopedic surgery cluster, which also has NPs and PAs, but they're typically providing, support for the orthopedic surgeries that are going on, or taking care of those individuals after and before they have surgery. And then if you want to dig in a little bit, you can look at clusters, for example, for pain management. So the two of the 3 most populated specialties within this cluster are interventional pain management and pain management, but you can also see the other individuals who are probably prescribing a lot of opioids. So if you wanted to identify, for example, occupational therapists that might be linked within this kind of type of medicine that's being practiced, you could go look and dig into more detail based on what this cluster is telling you. Okay, so that's it in a nutshell. There are standard limitations. Medicare Part D prescriptions are only those for the people who actually use Medicare Part D, and that's definitely not everybody in the US. For patient safety and protection, if the doctor does not provide at least 10 claims, then that data is completely removed. This is an atemporal analysis. It's based on 2015 data only, but there is public data from 2012 to 2016, so we could think about how our care practice is shifting over time. And then we have more work to do with respect to the neural network itself. Is the cosine similar, the rate similar that we should be optimizing or thinking about? Can we remove or formalize these extra loss terms that are helping us in terms of building our model? Do we need the autoencoder itself, or can we make this headless? Can we actually figure out the number of intrinsic clusters? Right now we're actually saying, oh, let's play around with K, find something that kind of matches our intuition about the reasonable number of clusters for providers. So that's it. Thank you very much.
Yeah, thank you, Jeremy. Really interesting. So do we have any questions? Yes?
Very cool. As far as using an autoencoder to try to have compressed representation and put that to a probability space, do you consider using something like a p-stochastic neighbor embedding, which kind of might be equipped with something that might be built in to kind of spread out the probabilities rather than having them just be stuck around one spot?
Yeah, so T-SNE is, some people believe it's great for clustering, some people believe it's terrible. It has some, if you go to, I think, Core or Stack Exchange, I can't remember, there's a classic page that says, it works great on things like MNIST under particular settings, and it fails for multivariate Gaussians, or two multivariate Gaussians that are partially overlapping. So I think that's kind of an open problem, but that's something we're definitely looking to explore because we can kind of switch in and out some of these lost terms.
So what is the main clinical applications in your mind?
So we're looking into, for clinical applications, I would say that we want to dig in and look at the opioid epidemic. So we've now identified providers who are providing a lot of painkillers, and we want to compare that against if we were just to do a standard like database filtering method. Take everybody who prescribes at least, this much oxycodone or OxyContin, and who does that give you? This may give you a better representation because it automatically encapsulates, oh, well, Percocet's probably pretty similar to oxycodone. Let's lump those in together. And it provides providers who cluster together with just kind of a general fingerprint or phenotype over all opioid disorders.
Fantastic. Any last question? No? Not for now. Thanks. Thanks, Jeremy. Yes. And then just asking the next two speakers, after this speaker, do we have them in the room too? Yeah, you are one of them? Okay, that's just to check because, yeah. Okay. So I think it's one paper about case-based maintenance of a personalized. There's also a paper about the role of usability engineering in the development. That's fantastic. So we have everyone here. Great. Just checking. Awesome. Work. Okay, so our next speaker is Xiaoxing Xu on automated pain detection and facial videos of children using human-assisted transfer learning. So I'm looking forward to that. Fantastic. Thanks.
Hi everyone, my name is Xiaojing Xu. I'm a PhD student from UC San Diego. This is a joint work with all these co-authors. So it's on automated pain detection in the facial video children using human-assisted transfer learning. So first let me start with the background. Why do we want to do automated pain detection? First, we know pain estimation in children is important to prevent both under and over medication. And currently, the most widely used method to assess clinical pain is patient self-report, but it has some limitations. For example, it's subjective, it's not feasible for infants and people with communication or neurologic disabilities. And it's been proved to be more useful for comparisons over time within individuals rather than comparisons between individuals. So because of these problems, people often distrust self-reports and focus on developing an automated pain estimation method. And that's also our goal here. To achieve automated pain detection, we first need to find some features related to pain. Of many choices, facial activities can provide rich information about pain. Like when you look at the two pictures, you can easily tell the boy in the picture on the left is having pain and the boy in the picture on the right is not. In order to efficiently and systematically investigate facial activities, people have searched for reliable facial indicators, such as facial action units, also called AUs. In this table, I'm listing the first 11 AUs. Each of them corresponds to some facial muscle movements. And through this link, we can actually find the description of each of the AUs and the corresponding movement. It's funny. So let's go back to our slide. Okay, so using this feature theorem, people have developed machine learning methods to recognize pain. And that's exactly what we are trying to do using AU's neural networks to recognize pain in videos. So next, let's look at our data set. We have 143 subjects. They are children who just had surgery. We collected data over 3 visits. Visit 1 within 24 hours after the surgery, visit 2 within 24 hours after the first visit, and visit 3 several days after the surgery, when the children were supposed to have no pain, have recovered, and have left the hospital. So at every visit, videos of the face were recorded while manual pressure was exerted at the surgical site. Then the rating of the pain level ranging from 0 to 10 was given by the child. Overall, 754 videos were collected. So after we collected the data, we started to extract AU features from the videos. We decided to use a software called iMotions to extract AUs automatically for each frame. Here are some screenshots I took. On the left is what you see when you open the software, and on the right is what you see when you use the software to analyze video in real time, and these are AU sequences. So other than the software, we also had a human coder to code AUs from the video. So at this point, we had 2 sets of AU codings, automated codings from iMotions and manual codings from the human. So now that we have features, we started to process them and do our machine learning. First, we should notice that we have AU values for each frame for the whole video. So the first feature dimension is huge. And so we calculate statistics such as mean, max, standard deviation, maximum, and so on to reduce the feature dimension from the number of frames times the number of AUs to the number of statistics, which is 11 times the number of AUs. And this is done for both automated and manual features. And then we obtain labels from children from their self-ratings. It's quite simple. We just follow clinical convention and label ratings from 0 to 3 as no pain and 4 to 10 as pain. As for machine learning method, we use a simple fully connected neural network with one hidden layer to classify pain and no pain. And we can use either automated features or manual features to do this. But we should also remember we want to make the whole pain recognition process automated. So in the end, we hope to recognize pain using only automated features. At this point, we are happy to find we have everything we need to complete our task. We have automated features, we have a model structure and labels. So we just go ahead and do cross-validation on our dataset and look at the performance. We use AUC, the area under the ROC curve, to evaluate the model. The AUC is 0.77. It's pretty good, but then we noticed something that might be a problem. So we noticed that all the pain videos were recorded in hospital, and most no pain videos were recorded in an outpatient lab. So we began to ask, is it possible that our classifier is cheating, learning the environmental differences between hospital and outpatient lab instead of pain and no pain? So it's quite possible because in hospital, the children lie in the bed, and in the outpatient lab, they sit in a chair. Although we try to make the angles of the bed and the chair to be the same, there still could be differences in head positions and lighting conditions, etc. So in order to tackle this problem, we decided to look at different subsets of the data, which have different environmental distributions, and we call them different data domains. So here is the way we define the 3 data domains. The first row in the table shows the distribution of all our data. Visit 1, 2 is in hospital in bed, and visit 3 is in outpatient lab in chair. All the pain data are in visit 1, 2. No pain data can be either from visit 1, 2 or visit 3, but most no pain data are in visit 3. So one thing to notice is that we only focus on visit 1, 2, which is D1 performance. So we define D1 to include pain and no pain in visit 1, 2. And we define D2 to include pain and no pain in visit 3. So the reason we only focus on D1 is because we only consider giving medicines to the children when they are in hospital. So in visit 3, we are almost sure they don't have pain anymore. So we don't need a machine to tell us the answer. So then you may ask the question, why, since we care so much about D1, why do we do visit 3 at all? The reason is, first, V3 consists of most of our no pain data. And more importantly, V3 no pain has higher quality than visit 1, 2 no pain. This is because in visit 1, 2, patients usually still have some pain, and even if a sample is labeled as no pain, it may still have a pain rating of 1 to 3. But in visit 3, no pain samples just have a pain rating of 0. So we say visit 3 have a pure no pain than visit 1, 2. So as a result, it will be easier for the machine to learn no pain patterns if we give it V3 no pain samples in addition to visit 1, 2 no pain in the training process. Our experiments actually also prove that when we train with all data, the performance is always better than training with visit 1, 2 data. So remember in the previous slide, we obtained an answer. So in the previous slide, we trained and tested with all our data, which is the first row. But from this slide, although we'll still train with all data, but we'll only focus on D1 performance. And our assumption made in the previous slide is that we are classifying in hospital versus outside hospital instead of pain and no pain. So if that's true, then we'll see that D1 performance will be much worse than D2 performance, because in D2, the two classes are different in environment. But in D1, the two classes are only different in whether there's pain. So let's look at the performance then. I'm showing the RLC curves for classification on each of the two domains. You can see that the blue solid curve corresponding to D1 is much lower than the red curve corresponding to D2, which is consistent with our assumption that the classifier learns the environment instead of pain. And D1 is actually not much higher than random. So now comes the problem. We have to use V3 in training because V3 samples are good in both quality and quantity. But V3 is also different in environment, and it's hard to force the machine to ignore that when it learns to recognize no pain. This is actually a transfer learning problem in which we train the model on the domain all data, but apply it on the target domain D1. The key to transfer learning is to find common knowledge between the two domains. And obviously, our model fails on that with the AU features extracted by the software automatically. This is because the software is sensitive to environment. So we started to wonder if the human will be more robust to environmental changes when coding AUs. Remember, we also have a set of manual coding, so we can just go ahead and try that. This slide shows the performance using manual features on the right comparing to automated features on the left. We can see the manual codings give us better performance in D1, which is the blue curve, and smaller distance between D1 and D2 curves. So we can say manual codings are not as sensitive to domain changes as automated codings. This is exciting, and we are also thinking about how to further improve the robustness of manual features. So at this point, we noticed that there are some AU codings coding the head movements, so we may want to ignore them. There are also a bunch of AUs irrelevant to pain, so we may also want to remove them. Then we were left with these 8 AUs related to pain. So you can take a look. And using only these AUs may help us to reduce noise and improve model robustness. And the performance is shown here on the right. The rightmost curve corresponds to menu features using only pain-related AUs, and it's even better than the middle one, which is menu features. So still, the D1 performs better than D2 performs better than D1. The reason might be D2 no pain has higher quality than D1, so of course D2 performs better than D1. So now we obtain pretty good performance with pain-related menu features, and the problem of transfer learning is solved. But remember how we wanted to design an automated pain recognizer. So we need to think what we can do with automated features. The thing is, although the automated features are sensitive to environment, we believe they contain all information to recognize pain. They may also contain all required information to predict the true AUs, which is coded by human coders. So here's our main contribution. We propose to map automated features through a subspace of menu features. Doing this, we are hoping to learn properties of menu features as well, including the transfer learning ability. Specifically, we trained a one-layer neural network to predict menu features with automated features. There are some tricks here. One of them is that since the dimensionality of menu features or pain-related menu features is too large, which is 88 to be learned by simple regression. And since we found that we can get pretty good performance with only 4 principal components with the menu features, we applied PCA to these pain-related menu features and mapped to only the first several principal components. So now let me quickly summarize what we have talked about so far. Our goal is to distinguish between pain and no pain with automated features, which is the below. So referring to the graph, we did one first to predict classes with automated features. And the performance on D1, the data set we care about, was not good. So we then did 2, and we saw that the performance was improved. 2 is using manual pain-related features to predict the class. So we proposed to do 6 and then 2. We first use 6 to predict automated manual pain-related features using automated features. Then we use the predicted features to do the classification, which is 2. So we can also do 5 and then 4, in which we map automated features to several principal components of the manual pain-related features. And then we use the predicted principal components to do the classification. And 5 and 4 seems to have advantages over 6 than 2, because 5 is easier than 6 to predict fewer features, and 4 and 2 are similar. So finally, we get the results using our transfer learning method. On the right is our original automated features result. In the middle is our pain-related menu features, and on the right is our transfer learning method. So we can see with the transfer learning method, we can obtain as good performance, the same AUC as using menu features. And but it's without menu features, so we can do it in real time, for example, without labels and so on. So, so it should also be noted that with this method, we only need to manually code a small portion of the data. And as long as the regression network is trained, it can be used directly for new data with only automated features. We did test our model on a new data set with only automated features, and the performance is improved from 0.69 to 0.73. So in the last slide, I'll go further into details about the 2 levels of transfer learning. So we know there are 2 steps to recognize pain. First, we use an AU extractor to extract AUs from videos. Then we use a classifier to classify pain and no pain using the AU features. And the AU is what distributed differently in different domains. So that's where we apply the mapping. So transfer learning can be seen to have been using both models. And this table explains why this is true. So in the first model, the AU extractor, we train our model in the source domain, some other data domain, and we apply this model in our data domain. So the output is not accurate, which is the AU features. In the second step, in the classifier, we train with all data, but test with only data domain one. So the input was distributed differently between the two domains. So we solved the domain transfer problem in both models by doing the same thing. We adjust the AU features, the distribution of the variable between them. And we do this by learning a map from automated AU features to AU menu features. So finally, our conclusion is we recognize differences in pain classifier performance across data domains and introduce a transfer learning model to map automated features, first for subspace of pain-related features, and then use the transfer learning transfer features for classification. This allowed us to leverage data from a source domain to improve classifier performance on our target domain. Okay, thank you for your attention.
Thank you. Yeah, I think we might just take one very quick question. I'm just looking around in case others have. Okay, yeah, go ahead.
So your data size is quite small, and data is unbalanced and highly correlated with the bandwidth rate. Have you thought of data augmentation? Like, for example, you can put faces in different backgrounds and generate output.
Yeah, so one way to make more data is to use data augmentation. And in here, we just duplicate the data, like the samples in the class, which has less data than the other, fewer data than the other. But it's a good idea to just use data augmentation.
Cool. Fantastic. Thanks again. Ooh, good. So, okay, so we have 2 more sessions to go. And our next speaker is Joaquin Massana. And he will speak about case-based maintenance of a personalized insulin dose recommender system for type 1 diabetes patients, I guess. Fantastic.
Good morning. I am Kim Massana, and I will begin explaining our board. There is a proliferation now of mobile applications that are trying to deal using artificial intelligence to the type 1 diabetes mellitus. So the mobile is something proper because you can easily collect, measure glucose level and physical activity through Bluetooth sensors. Some of these, in our case, as a insulin recommender, uses case-based reasoning, CBR, as a core of the application. Most of the existing applications uses a small set of attributes, like hour of the day or carbohydrates of intake, etc. So in order to maintain the case base of the CBR small, They are using simple techniques to do it. But in our case, we are collecting a lot of data, such as exercise, happiness, hormone cycle, alcohol, level of alcohol, etc. So in our case, we need techniques to maintain the case of base efficient. So new methods are required. Taking into account this situation, the objectives of the work are the following one. It's to provide case-based editing techniques for the CBR, insulin recommender we have, in order to first deal with numeric solutions, because the techniques we can find are usually for nominal solutions. So the idea is to keep the case base smaller and efficient, and in the same time capture the physiological changes in the illness, so in the subject. This is the concept drift. Before to continue, a bit of introduction in the case base. The case base uses past experiences in order to provide solutions for new cases. The case base, CBR, has 4 main steps. The group step, search past experiences that are similar to the new case. In the use step, the experiences or the solutions are adapted to the retrieved case, to the new case. The revise step corrects the proposed solution only if it's necessary, following some rules. And in the retain step, the system decides if this new case must be stored or not, according to some strategy. In our concrete case, the paper insulin recommender product for type 1 diabetes mellitus, in the retrieve step, the user will introduce all the context for the intake, like exercise, things I explained it. Then the CBR will search similar cases in the case base. In the next step, the user step, the CBR will propose a solution for this case. So it means to propose insulin to carbohydrate ratio, that means bolus, that means an insulin dose for this intake. Then in the revise step, the solution is revised according to some strategy. In this case, according to the postprandial minimum glucose. So we will monitor the sugar after the intake, and then we will capture the minimum. After this, the case is approved or not by the clinicians. And in the retain step, the last step, the case is stored and the similar cases are removed. This is how the system now goes. We propose a maintenance in the retain step. The retain step will be substituted with these 3 new steps. The retain, where the new cases are mentioned, the review, in where we will generate some scores related with the case base, and the restore step, in where we will manage the case base according to these scores. First, following the steps, the retain routine strategy. Here, when a new case is arrived, if there is a case with equal attributes an ICR, so the solution, then there is no need to store the both cases because there is redundancy. So the old case will be removed. But if there is a case with equal attributes but different ICR, the old case is removed because we are in front of concept brief. The illness is changing. Next, review and restore time analysis. Here, the cases will be statistically analyzed throughout time in order to search differences in the timeline. So searching if there is a concept brief too. So the main steps will be, first we will store the cases according to the timestamp. Then we will calculate the mean and the standard deviation of the solution, the ICR, through a sliding window. And finally, if we find significant differences, we will remove from the case base the old cases. And the last, review and restore, in this case, coverage and reachability analysis. We need a tool to say that two solutions first are equal, because the methods we will apply are for nominal solutions. So we need a tool to say if a solution is equal to the other. And we will use the accuracy in the pump. The accuracy in the pump we use to make the infusions to the doses of insulin has accuracy about half bolus. So we will translate these half bolus into the solution, to the ICR. Then we will say that an ICR is equal to another ICR. Then, now we can calculate different metrics. In this case, the coverage, that it's the set of cases that can be accurately solved by the target case. And the reachability, that's the set of cases that can be used to accurately solve the target case. Finally, we can use restore methodologies, like first we will test both in parallel in order to take a look what is better. First, the conservative redundance reduction, that is the CRR, and the iterative cost filtering. We will briefly take a look what means each one. Here in the CRR methodology, we calculate the coverage of all the cases. Then the cases are sorted in descending order of coverage, and we will add iteratively the cases in the new case base. But the cases of each coverage will be removed from the remaining cases. This is the CRR methodology. And in the case of the ICF methodology, it's simplest. We'll calculate the coverage and reachability, and then we will remove all the cases whose reachability is greater than the coverage. We perform simulations, experimentation, and the experimentation has the following features. We use it Padova as a simulator, MATLAB simulator. We use it in the simulations 11 virtual adults. And we make the simulations for 180 days and 20 repetitions. The glycemic range used was for the low level 70 and in the 180 milligrams per deciliter. The performance was evaluated, in terms of three main indicators. First, time in target. That means the time in which the user is inside the glycemic target range. Time above target, that means time in which the user is above the glycemic target range, and time below target. That means the time below the target range. And as I said previously, the analyzed methodologies are first, no method, no review restore, then the method using ICF, and then the method using CRR. Results. As you can see, in the left, we have the size of the case base, and for the 11 virtual users. So as you can see in blue, the no review method uses a high amount of cases, so it's less efficient and the case base is bigger. In this case, you have more information. You can see that ICF improves slightly the CRR method. CRR in green and ICF in red. Results in terms of health indicators. In the case of time in target, the CRR method improves the old method. That means improves no review restore. Except in the subject number 2, because the highest glucose stability, the glucose stability is really high, so it's hard to be improved, this user. And the CRR method improves slightly the ICF method. Taking into account time above target, the CRR method achieves similar results than the old method. and it's important because reducing the time above target, we will reduce the risk of long-term microvascular complications and long-term macrovascular complications. So the differences are really low. And it happens the same with the time below target. In the case of the SEER, the method achieved similar results than the old method. It's important in this case because reducing the time below target, we are reducing the risk of loss of consciousness, the seizures, or the risk of death. Okay, as a conclusions, we have a bolus recommendation system based on CBR that it's capable of providing accurate recommendations, but for having a really high amount of attributes, we need a system in order to maintain the case base smaller and efficient. So we proposed a technique in order to deal with this issue. The results demonstrated that our method is capable of maintaining the case base small and efficient, maintaining the level of accuracy in the predictions, trying to avoid the hyperglycemias and hyperglycemia, following the concept brief. So for future works, we are implementing some method of learning the relevance of each attribute. Thank you.
Thank you. Do we have any questions? Yes.
You explained that you throw away old cases in the case of concept drift. You actually want concept drift in your case base. Can you explain why you don't want to maintain same why you want this?
Why we need the concept brief idea? Yeah, because some illnesses like Parkinson or maybe Alzheimer evolutionate changes throughout the time. So the idea is to following the changes that the illness is having. This is the idea. Some infusions or dose of insulin can be accurate for one moment, but then the same patient through the years need more insulin for the same intake. This is the idea of following the concept.
Yeah. Good. I think, thanks again. Exactly. The next and last speaker for this session. Okay. And the talk will be about the role of usability engineering in the development of an intelligent decision support system. And Claire Martin will be giving this presentation.
Okay, hello. Hello, I'm talking about actually the same project that Joachim was talking about as well. It's part of the same work. So, yes, the role of usability engineering. I'm going to talk about 4 things. First of all, why should we care about usability? And then give some context, which is what the work that we're doing, artificial intelligence for diabetes, as was just explained. Then I'm going to talk about how we measure usability and some very preliminary results. Why should we care? Well, of course, there's no point us produce, but still the patient got a huge overdose. And the theory is that what happened was that because it was done on a calculator in the order in which it was performed, what happened was that instead of dividing by 24 at the end, they multiplied by 24, and both of them did it, and other nurses who were asked to do it made the same mistake. So if the people who'd made the technology, who'd made the infusion pump, had actually looked at how users use it, what the workflow is, how they use it in the workplace, there was no need to actually have that calculator intervention. It could have just been done on the interface, and that needn't have happened. So that's one of the reasons why we need to care about how people use our systems. Of course, for artificial intelligence, another issue can be trust. if people are going to hand over, for example, their dose of insulin to an artificial intelligence, they have to trust that it's going to give them sensible advice. And we can give them a certain amount of help with that, feedback with some data visualization to help them believe that they're getting the right answer. But even then, we have evidence to suggest that patients won't accept a dose if it's too different from what they normally do. So it makes sense actually to build that into your artificial intelligence, to actually not change things too drastically, too quickly, to be aware of what it is that will allow people to accept those changes. So just briefly to perhaps reiterate what Joachim just said, I'm working on the PEPPER project. This is the context in which this work is being done. And I'm from Oxford Brookes, so I'm leading the project and also responsible for usability. And the purpose of the project is just people with diabetes can't control their blood glucose levels because they don't produce insulin, so they have to take a dose of insulin frequently throughout the day, and the amount that they give themselves, they have to calculate, and it's very complicated. So that's what Joachim's AI is doing. It's telling them how much to give themselves each time. Just a quick overview of the system. So it reads in various data wirelessly into a central handset. The handset is either the handset for the Cellnovo insulin pump for patients who are used to having their insulin administered via a pump, or for patients who are used to having their insulin given by injection through an insulin pen, like the one at the bottom there. They can have the system on a mobile phone. And as I say, it reads in a continuous glucose level from the Dexcom sensor for physical activity, and also capillary glucose readings get read in automatically. And then inside the handset is the case-based reasoning that it's just been described to you. But also there's a safety system that uses model-based reasoning to predict adverse effects and detect faults, and that's being developed by Imperial. And all of that gets liaises with a clinical portal. So this is a rather busy slide, sorry about this one, but this is a summary of the usability engineering process that we're using in the project. We're trying to adhere to standards throughout. So I didn't mention it. I had it on the earlier slide, the 62304 standard for software development and the 62366 standard, which some of you may know about, which is about the application of usability engineering methods to medical devices. And in that standard, they define various terms, such as all the ones in capital letters are defined in the standard. And it just defines the process that you're sort of supposed to use. And it's, in a way, it's just like a standard usability engineering process, but there are extra features to take into account that it's being used for healthcare, and therefore safety is paramount. And the standard, the top table is a sort of summary of how the standard works. It's divided into 4 stages, and within those 4 stages there are 9 steps. And we've interpreted this in a certain way for our project, so it's not all prescribed within the standard. And the first part is about user research, so it's just gathering requirements really from focus groups and interviews. The second stage is the bit that's particular to usability for healthcare, and that's about safety, and it's about finding out about hazards and hazardous situations in order to work out what kind of use scenarios you need to test your system in to make sure it's safe. And in our case, we've used documentation produced by pump manufacturers to get these hazardous situations, but also there are a lot of publicly available databases. So, for example, in America, there's the MAUDE database produced by the FDA. In the UK, there's the MHRA database, and you can get a lot of data from there about how things have gone wrong to help you know how to design to avoid those features. And then perhaps the heart of the usability engineering process is the bit that's in red, the iterative design and formative evaluation, which is how you establish your user interface evaluation plan and execute that. So you do various iterative stages of evaluation and redevelopment of your system. And that follows a fairly standard procedure. So for usability, typically you have analytical studies which are done by experts prior to any tests with users, and then you'll have the user studies, and those are divided into ones you do in the lab and ones you do in the field. And the ones that you do in the field in this sort of case are a bit more complicated because we're using mobile devices and it's medical. So that makes it a bit more difficult. So just very quickly, because I don't want to run into a coffee break. For the analytical study, we used we based it on standard techniques. Keystroke level model and heuristic evaluation have been around for years. But we used slightly more modern variants, touch level model, because we were using a mobile device. And heuristic evaluation, we didn't use the original heuristics invented by Nielsen. We used some more recent ones that are done for mobile devices. And we used experts that knew about diabetes as well as usability. So that gave us some improvements to the system that we then fed into the next iteration, which was the empirical lab study. And again, that's fairly standard procedure, that you use your task model to get the patients to conduct various tasks, and then we filmed their interactions with the mobile device, and that's what the picture on the right is, a little video camera that we used, a bit like that one, to film their interactions on the mobile device that we could then analyse to get various metrics. So, for example, effectiveness is measured by task completion, efficiency is the time taken, simplicity is the number of errors, and then satisfaction is done separately through a questionnaire. We also had them to do a few questionnaires. The SAS questionnaire, again, is a standard technique. So there's nothing particularly novel about that. But then when it comes to the field study, that's where we have had to be a bit more creative, and we haven't got very far with that yet. It's still ongoing. But first of all, we decided to do, because you can't really, a field study typically might go to someone's workplace and see how they're using the system. But if people are taking the system home and using it at home and using it every day, you can't do that. So we did an in the wild study whereby the people they have an interview at the beginning and they're phoned up, and then there's a group meeting at the end to try and find out a little bit more about how they're actually using the system. And then we're processing all those interviews. And then finally, there'll be a large clinical study in the autumn for this project. And we're not allowed to interfere with that at all. The clinicians don't want us mucking up their outcomes. So for that, we've got to be completely invisible. And we thought we'd just use some analytics, Google Analytics, but we can't do that because it's a medical device and it doesn't talk to Google. So we've got some bespoke analytics library that we've written that's going to help us get some data there about how people use the system. Okay, moving swiftly ahead. I'm nearly out of time, I'm aware. So this is just a brief list of the tasks that we evaluated with the patients. PMA is the mobile application. We did a separate evaluation with clinicians on the desktop evaluation. The ones in bold are the ones that fared badly. Just very quickly, because I'm conscious of time. One example of a graph, we've got loads of data. This is an example of just the time taken graph, and the line in blue shows the tasks that were really bad, so we can tell where we need to make improvement. The red line is the task level model times, which are estimates taken from a paper. We think these were massively optimistic because they're the same sort of pattern as the users, but much less time. The SAS scale, we performed quite well. We were in the excellent range. We'd like to be up higher, so we're going to work on that. The In the Wild study, as I say, it's got various stages, interviews on entry, daily records and weekly interviews, etc. And we haven't analysed that data properly at all yet, but basically just to say that people are enthusiastic, they're learning a lot, and the feedback and visualization we're giving is getting some good feedback. So that's the end. So just to say, really, to finish with a bit of a summary, to say that conditions like diabetes have got, artificial intelligence has got so much to offer people with diabetes. If you look at the national statistics, they are massively, the population that's actually achieving the desired targets is tiny. In the UK, it's about 20%. Artificial intelligence can really improve this if you create it with users in mind in a way that they might use it. So I'd like to encourage everyone to work on it. So that's the end. Thank you.
Yeah, that was really interesting. And also, I understand there was a connection to the previous project.
Yes, I probably didn't answer as clear as I should.
No, that's very good. Do we have any questions? Yes.
So at the beginning of your talk, you mentioned specific AI-related usability issues, where if the dose recommended is too different from what the normal use would be.
Yes.
So do you use these features from your usability study in the cases that are being used to recommend things?
It's really a question for Joachim. Yes, so we found there was a previous study at Imperial, and they found that if the recommendation was 20% different from what they'd normally do, they just reject it. And so within our approval process for the cases, we don't let cases that are more than 20% different go in, do we? It's a discussion we need to have. As far as I know, we do take it into account, yes. That's the answer. But yeah.
Probably time for another quick question, if there is.
People want their coffee, I think.
Yeah, exactly, this coffee break. But you pointed out at the very beginning an important point about the accountability also of the system when people start trusting the system and so on. And that is actually a very important point that has been raised now. Also in Sweden, there were several discussions in Almedalen and so on. And I was just wanting to point to the ethics panel that we have tomorrow, so I'm sure it will come up there too. But do you have some discussions already on that topic in more detail too, like when it comes to ethics, accountability, trust, transparency of the system and so on?
Probably not nothing.
Yeah. No worries. Super interesting.
Ethics, the whole ethics, regulatory, it's all so complicated.
Yes, it is not the easiest of things.
Yeah. And getting approvals.
Yes, that's right. Yeah, great. Okay, thanks again. Okay, so this very first session will end now. We have coffee. I think it is down the hall from 10 to 10:30. At 10:30, we start again with the second session of today. And I believe Rafik Muhammad will be giving the next first talk then. So thanks for coming.
So yeah, coffee is in the main hall B. Don't leave your laptop here because there's no control of access, so people can walk in.